Welcome to today's class. I'm glad to have you here. Today I want us to look at photoelectric effects. Now, by photoelectric effects, we'll start by breaking these into two. Photo means light. Photo means light. While, of course, electric means electricity. Now, photoelectric effects is just a process whereby electricity is generated in the presence of sunlight or using solar radiation. So because of that, we can now go ahead to define photoelectric effect as the process by which electrons are ejected or liberated from the surface of metal plates. So, electrons are ejected from the surface of metal plate by a shine light of appropriate frequency. So, I want us to look at the shine light of appropriate frequency. Appropriate frequency. Now, or you can say sufficient frequency. Now, there are two things I want us to notice here. I want us to note that there must be frequency, and the second one, there must be wavelengths. There must be wavelengths. Okay, so if the intensity of that incident radiation, that solar radiation, if the intensity, if the wavelength of that incident radiation is too long, even if the intensity is from morning till night, nothing will happen. No electron will be emitted. For electron to be emitted, the wavelength must reach a certain threshold. The wavelength must reach a certain threshold for electrons to be emitted. If not, so it doesn't depend on the intensity of the solar radiation or the duration of the solar radiation. No, it depends on wavelength of the incident radiation and then frequency. So these two must come have roles to play. So if the wavelength is too long, nothing will happen. If the frequency does not reach that threshold, nothing will happen. If not, in fact, the only thing that will happen is total absorption of that incident radiation that will happen. So, for photoelectric effect to take place, the wavelength must reach a threshold. Frequency also must reach a threshold. That is why we say that here there must be appropriate frequency or sufficient frequency. Okay. Now, we now say that yes, maximum kinetic energy of an electron. So, the maximum kinetic energy of an electron depends on this two. Now, we now look at the kinetic energy. When the kinetic energy is plotted, if you plot a graph of kinetic energy, if you call it just a kinetic energy, but maximum kinetic energy in joules, if it is plotted against frequency in hertz, we'll obtain this graph here. If we plot it, this is a plot of maximum frequency, maximum kinetic energy, or you can say stopping potential, Vx. We'll look at stopping potential as we go on. So either stopping potential or the maximum kinetic energy. So if it is plotted against frequency, three things will come from here. The first one is, one, we'll have a straight line graph cutting the frequency as is at this point. So this point is the threshold frequency. This point is the threshold frequency. While the kinetic axis is here, we have intercepts here at this point. So here is our work function. Assuming we have here O and then we have here C, and we have here as K. So 3 deductions will come from here. The first one is right here. The first deduction that will come from here is that the slope of this, assuming I pick this point, bring the slope down, it must touch this. So if the slope touches here, we'll now say that slope of the graph gives the value of Planck constant K. So if you want to find Planck constant H, if you want to find the value of the Planck constant using this graph, we now have, of course, if you trace this point, maybe let's trace it here, let's say K2, and then here, trace it here, let's say K1 here. So now this is the vertical axis. For the horizontal axis, we pick the value, let's say here is F2, and then let's say here is F1. So we now say that slope is K2 minus K1 all over F2 minus F1. So slope of this graph will give the value of the Planck constant. That is the first deduction we take. Now the second deduction, but before that, please, for graph where this is plotted, where some problems are plotted using graph, please follow me in my next video, or check the link on the description button down below. Okay, so the second thing that will be deduced from here is we have the threshold frequency. Threshold frequency from it, that means, and of course, threshold frequency is nothing but that frequency above which, that value of frequency above which photoelectric effects will take place. Below it, no photoelectricity will occur. Okay, that is a threshold frequency. Now, of course, it is this value. Once you plot the graph, any point, any value here, pick it. It is a threshold frequency. So, we can say that threshold frequency, assuming we retain our K here, so we say OK, intercept OK gives the value of the threshold frequency, F0. Now, the intercept OC, the third thing I want us to deduce from here is that intercept OC from here to here, give this one here, gives the value of the work function. Of course, the work function is that minimum energy required to knock off electron from a metal surface. That is the work function. That minimum energy required to liberate or to knock an electron off a metal surface. So these three are these are the three deductions we can take from here. Okay. Now we move ahead. So if the energy, if solar radiation falls on a metal surface, remember we said that electrons are knocked off. But two things will happen there. The energy, that energy of that solar radiation that falls on a metal surface, the first thing it will do is to liberate the work function. The first part of it will give us the work function. That work function, the duty there is to knock off electron. If it knocks off electron, the remaining parts of that incident energy of that incident light, what it will do is to give that liberated electron, it will give it kinetic energy of half mv squared. So two of them put together will give us this kinetic energy. So the two things we have discussed about here now is the kinetic energy and the work function. So that will give us the Einstein's equation. So it will give us the Einstein's equation. So we have that the Einstein's equation is given as Einstein's equation, Einstein's photoelectric equation. We said that the energy of that incident radiation that falls on the metal surface, the first part, it will release the work function, and then that work function will liberate electron. If it liberates electron from a metal surface, the remaining part of this energy will now give it kinetic energy. So that kinetic energy is, so we now have this as an equation 1, but kinetic energy, this is kinetic energy. Kinetic energy is half mv squared, so mass of the electron there. Then W naught is hf naught, where f naught is the threshold frequency. W naught is the work function. If we put it in this equation, we now have that E is equal to hf naught plus half mv squared, equation 2. Remember that this E, energy is hf, so you can have it in this form. Or I can still, or we can now have that kinetic energy, when we say we can have maximum kinetic energy. Maximum kinetic energy is equal to EVS. This EVS, Vs is the stopping potential, so which will now give us hf minus work function, equation 3. So either we have, look at this, either we have this equation like max, either we have it like this, kinetic energy is equal to EVS, and EVS is equal to this. So either you say kinetic energy is equal to this, or you say EVS is equal to this. They mean the same thing. Where V subscript S, where Vs is the stopping potential. It is the stopping potential. Now, this stopping potential is a retarding potential or a negative potential. Remember, once electrons are emitted from the cathode, immediately this gives it kinetic energy. It moves straight to the anode. If you remove this stopping potential, that emitted electron will move straight to the anode. And once it gets to the anode will absorb it. So it is the function of this stopping potential to halt or to stop that emitted electron from reaching the anode. So because of that, we'll now say that yes, the stopping potential is the retarding PD or a negative potential of the anode, which is just sufficient to halt the most energetic electron from reaching the anode. So because of that, when I have kinetic energy is equal to this, and this is equal to this. Okay. However, any of these equations can work. So we have from equations 1 to 3 and more. We can still bend this equation to suit any problem given to us to solve based on this, and this. So we can now say, so before here we can now say that EVS is equal to H, or you can say EVS is equal to E, which is this, E minus, which is this, minus the work function. We can still have this one as our equation 4. So this E here is electronic charge. So one electronic charge, of course, one electronic charge is E is 1.6 times 10 to the power minus 19 coulomb. So that is the value of this E. So as we move on, we will see some problems that we'll solve using this problem. So let us solve one or two problems. Light energy 5 electron volts falls on a metal. Falls on a metal of what function? 3 electron volts. And electrons are liberated. What is the stopping potential? So we have the light energy. The energy of that light is given as 5 electron volts. Falls on a metal of what function? Now the work function E naught, W naught is the 3 electron volts. And they said, what is the stopping potential of the emitted radiation? Stopping potential of the emitted radiation is not given. And of course, the only equation that will help us to do it is this equation. So, which will now give us EVS is equal to E minus work function. So, EVS will give us E is a 5 minus 3, which will give us 2 electron volts. Remember, this is EVS is equal to 2 electron volts. Now, divide both sides by 1 electron volts. If you divide both sides by 1 electron volts, we now have that, yes, V sub S is 2 volts. So we now have this can take care of this, or divide both sides by this. If we do that, we now have that the stopping potential is 2 volts. JAMB does not joke with this problem. Okay, we'll take the next question. And this one says, a metal has a work function of 3 points. A metal has a work function of 4.37 electron volts. 37 electron volts. Calculate its threshold frequency. Calculate its threshold frequency given that. So this is the work function. So let me clean up the watch. So from here we have that the work function is given as 4.375 electron volts. Its threshold frequency is that. So threshold frequency, which is F naught, is not given. And then the next thing given to us is H equals 6.6 times 10 to the power minus 34 joules seconds. 1 electron volts is 1.6 times 10 to the power minus 19 joules. Okay, so what do we do with this? Since the question says calculate the threshold frequency, F naught. So of course, recall that W naught is H F naught. And we're looking for F naught. So F naught will give us, so we now have that F naught is W naught all over H, which will now give us W naught 4.375. Remember, because of these electron volts and it's given to us, so we put it times 1.6 times 10 to the power minus 19 all over H. 6.6 times 10 to the power minus 34 joules. So which will now give us, by our calculation, we have 4.375 times 1.6 will give us, so we have 4.375 times 1.6. 1.6 times 10 to the power minus 19 all over 6.6. So everything will give us 7 times 10 raised to the power. This time is 7 times 10 raised to the power. So if we multiply this 10 minus 19 all over 6.6 times 10 raised to the power minus 34. Now this over this. Remember, this is a high index numbers, so be careful with it. We have 7 over 6.6 times 10 raised to the power minus 19. If this minus crosses over, it changes to plus. So we now have 7 over 6.6 will give us 1.1 times 10 raised to the power. Now, minus 19 plus 34. It will give us 15. So we now have our threshold frequency is 15 Hz. So that is the threshold frequency of that emitted radiation. Okay, we take another question as well. And this question says, a metal is illuminated with a radiation of energy. A metal is illuminated with radiation of energy 6 point. Energy 6 point. This is the energy 6.88 electron volts. If the kinetic energy of the emitted radiation is 1.5 electron volts. Calculate the work function of the metal. Calculate the work function of the metal. And of course, since this question, this one is very, very simple. All you need to do is you can say energy is equal to work function plus kinetic energy. So make work function the subject. Work function becomes, so this one will move over here, E minus kinetic energy. So work function will now give us, the E is 6.88 minus KE. KE is 1.5. Therefore, the work function is given as 6.88 minus 1.5. The work function is given as 5.38 electron volts. Now, if the answer, if it's not BJ, if you don't see it, that means they will give you the value of 1 electron volt. If 1 electron volt is given to you, please go ahead and substitute it. But for this question, electron volt was not given to us. So since it's not given to us, we take it that way. Okay. An electron was emitted from a metal surface with kinetic energy. 1.6 times 10 raised to the power minus 18 joules. If the threshold frequency of the metal is 4.5, if the threshold frequency of metal is 4.5 times 10 raised to the power 14 Hz, calculate 1, the work function, and 2, the stopping potential. Okay. Now we have these constant values given to us. The constant value given to us are H, 6.6 times 10 to the power minus 34 joules seconds. And we also have that one electronic charge is given as 1.6 times 10 raised to the power minus 19 coulomb. So these are the questions given to us. So we now have, having this, how do we solve for the work function? The first one, work function. Remember that the work function is HF naught. Because we are given the threshold frequency and we have this, so we can as well say that work function H is 6.6 times 10 raised to the power minus 34 multiplied by the threshold frequency. which is 4.5 times 10 raised to power 14 hertz. Now if we do that, we will have, remember the rules of indices, 6.6 times 4.5 times 10 raised to power minus 34 plus 14, which will now give us, so the rule of indices says add the index numbers and multiply the basis. So we have 6.6 times 4.5, and it will give us 29.7 times 10 raised to power minus 20. Of course, yes, this is minus 20. So which will now give us that the work function is 2.97 times 10 raised to power minus 19 joules. So that is the work function. Now for the stopping potential, how do we solve for the stopping potential? The stopping potential Vs, EVS is equal to work function minus, of course, from these formulas we have there, we have that this is equal to this minus this, and then we have energy. Given the energy, kinetic energy was given to us. So since the kinetic energy was given to us, that means we now have that EVS is equal to maximum kinetic energy. Maximum kinetic energy. Of course, look at this formula. Now from here, we can make V as the subject. So if we make V as the subject, we now have that Vs is equal to maximum kinetic energy, KE max, all over E. And it will give us the kinetic energy here is given as 1.6 times 10 raised to power minus 18 all over. The one electronic charge was given as 1.6 times 10 raised to power minus 19. Okay? Minus 19. So which will give us, and of course, this cancel this will give us 1. So Vs is equal to 1. And if you send this one up, you now have minus 18 plus 19 will give us 1. So 1 times 10 raised to power 1. And of course, anything times 10 raised to power 1 is 10. Therefore, we can now say, we can go this way that the stopping potential is 10 volts. So 10 volts, that is our stopping potential. Okay, there are so many questions we can lay our hand on. But the last, we'll take this one, the last but not the least, or maybe I'll give it to you to solve as an example. Okay, now we'll take as a work function of 3 times 10 raised to power minus 19 joules. The maximum energy of liberated electrons when it is illuminated by light of frequency, this is dash. Now we have the Planck constant given to us. So this question, and of course I have solved so many questions. Please, using the same idea, how do you solve this? And if you have questions, please do well to hit the subscribe button. If you have questions, please ask me down there in the comment section, or you can hit my WhatsApp line and then send the question there. I will be able to answer your question there. But for now, please solve this, and if you are done solving this, you are expected to get 1.422 times 10 raised to power minus 19 joules. So this is the expected answer. This is the answer expected you should get. So if you get any contrary answer, please chat me up and then ask me why you are not getting this answer. Please, if you really find this lesson helpful, hit the like button, give it a thumbs up. Tell me how you feel about this lesson in the comment section. And then if you needed to give me tea, please, or you can give me snacks. There is an account. You just look for my account and then you give me that from there. Thank you very much. Stay tuned to the next video. Thank you.